to episode 6, Multivariable Physics. Today I'm going to be talking about the center of mass and the center of mass motion. So let's think about what center of mass is, what does center of mass mean. Suppose we have a collection of particles, right? Each particle is going to have, so if we have an origin here, each particle is going to have some vector. So every particle has a mass. It's in brown. Every particle has a mass. And every particle has a vector pointing to it from our origin, right? So every particle has an M and an R, right? That makes sense. So the center of mass is going to be the weighted average. So first of all, some intuition. Let's think about what the center of mass even is geometrically. If we had a bunch of objects of varying masses, suppose we had a point right in the middle. Now we had all of these sort of wires, right? And then we had some sort of tension force pulling the object in, based on the pulling the object in based on like proportional to the weight. So obviously if M is, so the greater the weight, right, the greater this tension force T, right? You can kind of imagine it like this wire system. And what's going to end up happening is eventually this dot is going to settle in some equilibrium position here, right? For example, and this position is going to be the position where all the tension is equalized, right? Where no other sort of wire is exerting more force than the other. And that's basically and that point, okay, this point is going to be the center of mass. And I'm going to label that with a big capital R, right? As opposed to just the regular R for position. So, how do we calculate the center of mass? Well, it's quite simple. All we need to do really is take, we're going to take the total sum of our particles, so Mi times Ri. So we're going to take a weighted sum of all of our particles for n particles, and then we're going to divide that sum by the total mass, and then here M is equal to the sum of M sub I from I to N. That's what that's going to be. And this is going to be equal to, this is going to be equal to R, C-O-M, center of mass. Okay, so what exactly can we do with this? Well, we can do obvious, vector stuff with this, or because this is a position, maybe you want to think about, well, what happens if all these masses are moving, all these objects are moving, right? Maybe they're moving in different directions, right? Maybe there's forces acting on these objects. What happens to the center of mass? So we can think about that. We can find the velocity of the center of mass, and to do that, so I'm going to call this V is equal to R dot, right? And so we know that this is going to be equal to D over dt of this massive sum of I, M-I-R-I over M, and that's just equal to the sum of M-I R-I dot. And so that's going to be equal to this. And one thing we can notice from this is equal to M-I r dot, right, is, this is the velocity, right, which is essentially saying the sum of all of our momentum, sum of the momentum of all of these particles over m is going to be this velocity, right? And so what is that going to give us? Well, this is going to give us, we have here, we have r dot is equal to net momentum over m. And let's think about what is the momentum of the center of mass? Well, this is going to be equal to our total mass times the velocity of the center of mass, right? And we can rearrange this equation here, bring this m up front. We find m r dot is equal to the sum of all our momentum, or momenta, and what we notice, these are the same. So what does that, what can we conclude? That the momentum of the center of mass is equal to the sum of all the momentum in our system. Okay. Now, okay, that's cool, I guess. But how can we? What does this tell us? Well, we're going to use an interesting identity here, right? So hopefully you should be familiar. I think I did this in the first episode, where force equals change in momentum, right? Well, let's think about what happens if, well, let's think about Newton's first law. F net is equal to m a, right? What is, what is going on here with this? If we do this for all of our particles, right? So this is going to be the sum of all of the forces on our particles, right? So the sum of all the forces on particle I, right, is equal to F net. Well, this is the same as saying the sum, meant I, of the change in all this momentum is equal to F net, right? And what we've already shown is that, well, we know that since we know that this is linear, we can pop this d over dt outside. I n pi equals F net, and we already show that this is equal to the center of mass, right? And so what we find is, okay, well, F net is just the change in the momentum of the center of mass. And I'm not going to write COM, but actually, I will. Yeah. Right. So we find that the total sum of the forces is equal to the change in the center of mass, right? So, this is pretty much the conservation of momentum, right there. Since we know from Newton's third law that that all of our forces are conserved in a closed system, F net is equal to 0, right? Which means that which implies that the change in the center of mass is equal to 0. So the momentum of the final momentum of our center of mass is equal to the initial momentum of the center of mass. Regardless of what happens in our particles, we could have a bunch, like maybe 3 particles at the start. We're going to have some center of mass here, and then that is going to transform, and then something's going to happen. Maybe these particles collide, these combine, maybe a piece falls off here, right? But we're going to have a brand new center of mass, right? And the momentum P is going to be equal to P, right? Final and initial. These are the same. And so we can use this in collisions and things like that. And that's pretty much the conservation momentum right there. So, I think that's about all the time we have. See you in the next video when I'll start talking about angular momentum.